let's just say there'll be a lot of emails. Okay. All right, let's get started. Welcome to Lecture 2 in Steel Design. I'm assigning the first homework assignment today, but I would say relish it. This is, without a doubt, the easiest homework assignment in this course, because what I'm basically going to be introducing you to is the concept of load combinations. And so I'll go ahead and tell you exactly what the homework consists of. And it'll be due Friday. But the long and short of it is, what you do is you have a series of loads, and then you basically apply your load factors and load combinations and report the maximum factored load to Blackboard. How many of you have had concrete design? So are you familiar with the concept of 1.2 dead plus 1.6 live? I would hope that you've done that in there.
Maybe, but I can't remember those numbers off the top of my head.
1.2 dead plus 1.6 live? That's like the money.
Oh yeah, that.
I was about to say, like, what'd you do in there? So I'm basically introducing you to load combinations, and you'll understand what that means after the lecture today. I want to talk a little bit about logistics. So the attendance grades are up to date and on Blackboard from Monday. I have recorded Monday's lecture. It's on the YouTube playlist. I am recording now. It will be on the YouTube playlist. And then Friday at 11, Friday's lecture will go live on the YouTube playlist. So, as I mentioned last time, Friday, we will not be together in person. That will be a pre-recorded lecture. I want to talk a little bit about the content of that lecture, and I want to talk about that in concert with the great manual purchase saga of 2022. So, I know that there have been some technical issues and whatnot with manual purchases. I pulled the survey that we did on the Monday, and what I got from that was that 6 students had technical issues and another 5 had yet to purchase it. Everybody else was good. But again, I know that there have been a number of technical issues with the manual purchases and whatnot. I have posted some details that I got from AISC on issues with manual purchases. They gave some background and whatnot. One of the pieces of info that they did put in their sort of generic feedback or suggestions is that maybe you need to wait until the coupon code is active. But our coupon code is active, so I know that's not the issue. What I would do is I would suggest, first off, if you have not yet purchased the manual, or if you have not yet done that, I really would start that process as soon as possible. When you create your account with AISC, make sure that you create it using your marshall.edu email address. Let me turn my phone off here. In other words, do not use live.marshall.edu, because the way that the coupon codes are structured, at least this time, they are tethered to the university, and so they're looking for at marshall.edu, not at live. There are a series of technical troubleshooting suggestions that they gave. My suggestion would be to give all of those the college try. If they do not work, reach out. They gave an email address for everybody to reach out to, and they will work with you one-on-one to get your manuals purchased. So the homework assignment that I'm assigning on Friday, excuse me, I had some peanuts earlier. The homework assignment that was on Friday would normally be due on Wednesday. I have decided to shift that due date to the following Monday. So the homework assignment that I assigned Friday is not going to be due until January 24th. And I'm hoping that gives everybody enough time to work through the technical hiccups and whatnot with the manual purchase and get that assignment done. That assignment is also incredibly easy. The real purpose of that assignment is just to get you to open up the manual and look up some values. So I might ask you, like, what is the flange width of this, or what is the warping constant for this shape and whatnot. And I go through sort of how the manual is organized and whatnot in that video. In fact, that's what Lecture 3 is really all about, is the manual. That's kind of what it is. Let's see, do I have anything else? I don't think I have anything else in terms of logistics. Oh, I did want to mention something else. So one thing I am going to do for the 2 assignments that I assign next week, normally I would not place the dimensions from the manual on the assignment. But given the technical hiccups, what I'm going to do is for the assignments next week, I'm going to give you the necessary lookup values from the manual so that if you're still waiting on your manual purchase, you're not going to be disadvantaged to get the manual and whatnot. Does that make sense? So I'm not going to, I don't want to hold up class, but I'm not going to punish those of you who weren't able to get the manual because of technical inconsistencies. Sound good? All right, any questions moving forward? All right, today I want to talk about breaking things. Let's talk a little bit about breaking things. Okay, in order to discuss this, I want to recall sort of the one definition that we, or the one term that we introduced during the last lecture. And that term was this concept of a limit state. So a limit state is a condition that we as engineers define that we want our structures to achieve. And so that can, I mean, there are a series of conditions that we can define. So for instance, let's say we're talking about beams, right? So we can define a strength limit state, and the strength limit state says that the beam must have enough moment capacity. Like it cannot fail under the maximum moment under the moment diagram, or it must have enough shear capacity, right? We don't want the beam to fail under the maximum shear on the shear diagram. Very rarely do we have steel structures comprised of a single member. More often than not, we have multiple members joined by connections. So we will have a series of limit states associated with the strength of bolts and the strength of welds and the strength of the base material those connectors are adhering to and whatnot. And so there's oodles and oodles of limit states associated with strength and safety. And those are kind of going to be what we talk about today. That's kind of be our focus, are these safety-related limit states or these strength limit states. But it is worth mentioning that there are also a host of other limit states that have nothing to do with whether or not the structure is going to fall down and kill somebody. They have to do with whether or not the structure is performing its day-to-day intended functions. We call those service limit states. So while there are some exceptions in some arenas, like there are service limit states in bridges where maybe some of the load factors aren't one, but more often than not, so today we are going to talk about what are called load combinations and load factors that are intended to be applied to the strength limit states and whatnot. Whenever we're dealing with strength limit states in this course, which is honestly what we spend most of our time dealing with, we are going to be factoring the associated loads. But whenever we're dealing with service limit states, we will not, okay? So as an example, and I can tether this to a concept that you all had if you took reinforced concrete design with Dr. Zatar last semester, when you dealt with moment capacity and shear capacity, you had to factor the loads, but you did not have to do so when you were looking at deflections and cracked moment of inertia. You didn't use factored loads then. It's because those aren't strength considerations. If the beam deflects too much, doesn't mean it's going to fall down and kill somebody. It just means it's not performing its day-to-day intended functions. Okay? Does that make sense? Okay. All right. Let's talk a little bit about factors of safety. How many of you have heard of this term, of a factor of safety? Good. I would hope by now that you've at least been introduced to this concept of a factor of safety. So let's keep concepts simple, okay? And I'm going to relate many of the concepts that I discuss associated with factors of safety to one of these tables. So let's say I'm feeling rather destructive. I like breaking things. My general philosophy is any day with controlled demolition is a good day. So here's this table, and I take it down to the Advanced Materials Testing Lab, and I say I want to fail this. How many of you have heard of, there's a YouTube channel, it's like the hydraulic press channel, you know what I'm talking about, where the guy gets 3 million subscribers, and all he does is he takes fidget spinners and snow globes and just puts it in a hydraulic press and breaks it. You know what I'm talking about? How do you get 3 million subscribers or something like that? It's still kind of awesome, though. But anyways, so let's say I'm feeling rather destructive. So I take one of these under a similar, servo hydraulic actuator, and I start applying load until I snap this thing in half. Boom. Okay? Let's come up with a number. Let's say that this fails at 800 pounds. So I can stick 800 pounds right smack dab in the middle of this thing, and it will snap in half. Let me ask you a question. If I go to Walmart or IKEA or whoever supplied this table, there's probably going to be a little warning label either somewhere on the table or maybe in the instruction manual. How many of you have ever bought the particle board furniture for your entertainment center or whatnot, or your nightstand from Walmart, and there's the little label that says warning, load or force may not exceed pounds. You know what I'm talking about? Now, what did we say? 800 pounds? Is that what I should put on the label? Probably not, right? Maybe what I ought to do is back that off a little bit. Maybe what I'll do is I'll tell people 400 pounds. I know that this table will fail at a load of 800 pounds, but I'm going to tell consumers don't put more than 400 pounds on it. What I have done is I have utilized what's called a factor of safety, a ratio or a factor that describes the relationship between what I might call a nominal capacity and an allowable capacity. But there is a difference between how much force will actually cause this thing to snap in half versus how much I'm going to tell a consumer to use. Make sense? Now, you can look at it one of two different ways. It doesn't really matter. Okay? One way of looking at it is to say the capacity of this table is 800 pounds, so its allowable capacity is 400 pounds. That's one way of looking at it. A second way of looking at it is to say, I'm going to tell consumers that the capacity of this table is 400 pounds, so I'm going to design the table for a load of 800 pounds. Whether you are reducing the capacity or augmenting the load, the effect is the same. It's still a factor of safety of 2, right? Does that make sense? I'm going to ask a rather basic question. I want to hear what you say. Why do we use factors of safety? Like, why? Well, but why is it safer? I don't know. Why? If it fails at 800 pounds, why don't I stop it at 800 pounds? Like, why?
Factors, so like, if something does happen where the object will fail, then, or in the theory where it would fail, it won't actually fail.
So,
Does that make sense?
you're saying that you don't know what's really going to happen. Am I simplifying that a little bit too much, or?
It's kind of like, you said it the other day, like, whenever like you're using like trusses and everything, if you just make everything massive, it'll work.
Mm-hmm.
But that's too expensive. So it's a small scale of just making it a little bit bigger.
Okay. All right. Does anybody else? Because I'm gonna twist that a little bit with another example, because you're not too far off. Does anybody have anything else they want to sort of add to that in different perspectives?
Maybe like wear and tear, so deformation over time. Where you're going to have a little bit, maybe like sag or something before you get to the fail point.
That's a good point. That's an interesting concept. Now, let me say this. What you are talking about is 100% something that we have to account for in structural engineering. We do it differently, though. We do not do it through the use of factors of safety. We just assess different limit states. For example, those of you that have had reinforced concrete design, probably when you did deflection assessment, you know that there is a difference between immediate deflections and deflections in the long term, right? And you have to compute effective moments of inertia. Over time, the reinforced concrete beam will crack more. It changes the moment of inertia, you get increased deflections. But then there are also material-related phenomena like creep and what have you, that the behavior of the concrete changes over time, right? That is a time-dependent phenomenon that we must account for, okay? Another thing that we have to account for in steel design land is the concept of fatigue, right? You got a soda can, right? Or your engineering student staying up late, you've got a Red Bull can or a Monster can or a V8 Energy. Oh, could have had a V8. Anybody get the commercial? Thank you. Okay. And how do you rip the tab off that can very easily? Take it. And after a while, it kind of gives up, doesn't it? The tab just sort of gives up. Now, if you were to take a microscope and look at what you're doing there, what you're doing is you're introducing micro cracks in that joint. And the more that you do that, you start opening those cracks up a little bit more. So you start reducing the cross-section that can resist that load. And over time, those cracks propagate, they grow and grow and grow, and they go. That's a concept in a metal phenomenon called fatigue, right? Now, what type of engineering system do you think gets loaded, unloaded, loaded, unloaded, loaded, unloaded throughout its design life? Bridges, there you go. And so in bridge engineering, we have to assess conditions related to cyclic loading. And there are oodles of discussions we could have about that. What is the difference between low cycle fatigue and high cycle fatigue? How do we assess finite life conditions versus infinite life conditions? And what infinite life means is once your traffic count gets crazy, the capacity sort of teeters off, and you just use that as your load. So, like, you know, you might design a bridge out in East Lynn for finite life, but you might design a bridge on 3rd Avenue for infinite life because it's just got more traffic, right? Does that make sense? What do we put on the roads in February in the state of West Virginia? Salt. What do you think salt does to steel and concrete decks and what have you? Causes all sorts of corrosion and whatnot. So we have conditions that we have to meet. The reinforced concrete engineers like to use cover requirements, right? The rebar has to stick some amount in between the surface of the concrete and inside. And that cover distance changes depending upon whether or not it's a beam inside a building or it's a pier in Miami, right? You might use 4.5 inches of cover in Miami, but inside of a building you might use 1.5 inches because you don't have to worry about exposure to the elements inside a building like you would in the salt air near the southern end of the country. See what I'm talking about? And steel land, we have to deal with corrosion protection systems. We have paint, we have galvanization, we have weathering steel, and what have you that we utilize for external applications, right? But that ultimately, though, that doesn't really get to why we use a factor of safety, okay? And I want to talk about, now, your first example was closer. And I want to talk about the concept of uncertainty, okay? I want to talk about uncertainties. How much did we say that the hydraulic press channel was going to break this table at? 800 pounds. So that means that this one is going to be exactly 800 pounds. Wait, no, it's not? That's right. That's exactly right. They are different tables. In fact, if I was feeling very destructive and I wanted to break every table in this room, I would probably not get 800 pounds for every single one of them. This one might be 810. This one might be 785. This one might be 846. This one might be 730. They might hover around 800, but there would be a spectrum of responses, right? Would you agree with that? Like, that's just reality. Let's start quantifying that. What am I talking about? Now, what did I say on day one? What did I say was the fundamental equation that we're going to be dealing with? We're going to be looking at it from two sides of the equation. We're going to be looking at loads and resistances. Resistances are what I'm talking about here with the table, okay? Resistances are measures of how much load a system can withstand before it fails. What are the uncertainties associated with resistance? What is the top of this table made out of? This is wood. Wood is an organic material, right? You tell me the properties in this wood panel are the exact same as the properties in this wood panel? Of course not. There's going to be variation in material quality, even in steel design land. Steel is a material that is much easier to qualify in terms of what I would say is uniform performance. Steel is a manufactured product, right? It's going to have more certainty in its behavior than even something like concrete, right? Concrete is mixed on site, right? I still think that the West Virginia DOH, how many of you have had 321? C329. I still believe that the West Virginia DOH, in their design manual, their mixed design manual for proportioning concrete, need to account for a certain percentage of empty skull cans inside the concrete mix. How off am I? It's accurate. There's a meme that goes along with that. I just need to find the right one, you know.
Maybe account for the amount of back evidence that's on it.
There you go. You know, there's organics inside there. You know, the empty Mountain Dew bottles, you know. Because that doesn't happen in the abutments, does it at all? When they're doing the fill, you know, McDonald's wrappers, that doesn't happen at all. I'm kidding, not really. I'm kidding. I'm kind of joking, but the point I'm making is that even under manufactured conditions, there are variations in material performance. There are also variations in the fabrication performance. Okay, these tables, let's talk about these tables. I love using these tables as an example, because do you think a human being fully was responsible for the complete creation of these tables? In other words, like there's a tree, and then, I don't know, a human being started punching it enough like it was Minecraft until it became this flat table. Or do you believe there were some machines involved in the processing of the wood and the drilling of the holes at given locations? You see what I'm talking about? What I'm getting at is, even though there were machines involved in the construction of these tables, and that these tables were generated in a industrial setting, if you were to take a laser micrometer scanner and compare, so like underneath this, there were holes that were drilled to connect the legs and whatnot. They're going to be a little off, right? The machine that drilled the holes might be precise to within 1/100th of an inch, right? So if you actually looked at them, they're off a little bit, right? That's what machine tolerances are for, right? Here's the other thing. I was a betting man. These tables came in boxes, and somebody from Marshall University Physical Plant or the supplier put some of this stuff together. Some of it was pre-assembled, and some of it was put together by a human being. Are you telling me every single nut, bolt, and screw associated with these tables were erected with the exact same torque, the exact same tightness? Of course not. There are uncertainties associated with the resistances, okay? This is what I'm talking about when it comes to factors of safety. We might say that the factor of safety associated with this table, or we might say that the capacity of this table is 800 pounds, but we have to recognize that there are significant uncertainties associated with that value. And we don't know whether or not that's really the number, which is why we apply factors of safety. Now, the problem with a factor of safety is, don't get me wrong, factors of safety are intended to address uncertainty, and in my opinion, they are necessary. My problem with ASD, and so that we're clear, the concept of allowable stress design is, here's your loads, here's your resistances, just a factor of safety, just a single value. That's what ASD is, a single factor of safety encompassing the entire problem. My issue with ASD, and a lot of structural engineers' issue with ASD, is that it treats the uncertainties all the same. I propose that the uncertainties associated with resistance are just different than the uncertainties associated with wind, or with loads. And I want to use wind as an example. If I open up the newspaper, which nobody ever does that anymore these days, or if I turn on WSAZ, or if I get on my phone and get on Twitter or whatever, I'm going to, whatever medium you choose to define, there's going to be an app that can tell me the wind speed today, right? Right? And I can open up my my Engineering 318 fluid mechanics book, break out Bernoulli's expression, right? Wind is a fluid, take the unit weight of air and go, wind's going this velocity, that turns into this pressure on the building, right? Pressure, load, boom, forces. You didn't think I'd be talking about Bernoulli's expression here, or Bernoulli's equation here in steel design, would you? It's crazy. But the base wind speed equation actually does come from Bernoulli's. I think it's here in the slide, and I'll show you it here in a little bit. But But the point I'm making is tomorrow the wind speed is going to be different, right? The day after that, the wind speed is going to be different. And the same is true of all of the associated loads that would go on a system, right? We are a live load inside this room. When we leave, there's going to be another class that comes in here. It's going to be a different set of live loads, a different set of forces and whatnot applied to the floor. I propose that it is a different probability distribution for the strength of the table under the hydraulic press than it is for the wind loads, than it is for the dead loads, than it is for the live loads, etc. So we need to treat them separately. Instead of having just a blanket safety factor, we need load factors. We need resistance factors. We need to deal with them scientifically and deal with them separately. We need load and resistance factor design. That's what LRFD is. What LRFD does is it factors the loads separately from the resistance. We have separate safety factors, if you will, for the loads, and we have separate resistance factors for the strengths. The load factors tend to be larger than 1. The resistance factors tend to be less than 1. The idea is that we've got some loads, we've got some resistances. Let's up the loads a little bit. Let's lower the strengths a little bit based on their inherent uncertainties and based on their probabilities of failure. And let's design structures such that they have uniform levels of safety. Now, here's the thing, okay? And this is something that you got to wrap your head around, okay? Has everybody in here had stat 345? Okay, all right. So let's look at the tables, for example. Let's go back to the tables expression. What we have, 800, 810, 780, 830, right? I could break every table in this room, and I could collect that data. And I could compute the mean of that data. I could compute the standard deviation of that data, right? And I can map a probability distribution to that data, right? So that I could predict strengths based on the mean and standard deviation, right? A common probability distribution is the normal distribution. How far does the normal distribution extend on either side? What's that? Well, the bell curve, it goes on forever. Either end, right? You know how the bell curve goes? It goes from infinity or negative infinity to positive infinity, right? See, here's my point. Probability distributions go on forever, right? And I propose that we can map, we're not going to get crazy into the statistics. I just want to understand the ideas. We can map the resistances to a probability distribution. We can map the loads to a probability distribution. See, I propose there is no such thing as a perfectly safe structure if you think about it in those terms, right? Because if resistance distributions go on forever and load distributions go on forever, there is conceivably a possibility, a region, where the loads would exceed the resistances, right? What I'm saying is, with a little bit of mathematics and precision, we can define that overlap region and minimize it, such that when we utilize LRFD, we are designing structures with a uniform level of safety. And so the load factors and the resistance factors that we utilize have been calibrated to such an extent that they generate structures of uniform levels of safety. And when I say that when we design structures, there's a probability of failure, it is so incredibly low that should you design appropriately, your structure is not going to fail. That's not going to be an issue. LRFD tends to result in more efficient designs, more economical designs, and more uniformly safe designs. So it's really sort of the go-to. In steel design, you have the option of ASD and LRFD, but in concrete design, you don't. We just use LRFD. We call it ultimate strength design, but it's basically the same thing. So in LRFD, we deal with factored loads and factored resistances. So what we do is we have nominal resistances and nominal loads. So let me kind of illustrate what I mean here on the board. So for resistances, and everything I've got here on the whiteboard's here on the screen, so you're not really missing anything. But the first thing we might do is compute a nominal resistance. And the nominal resistance might be akin to the 800 pounds that I was talking about here, right? Take the table, it snaps in half at 800 pounds. With me so far? Now, instead of just using a factor of safety of 2, what we might use is a resistance factor. We use the Greek letter phi for that. And so we might use a resistance factor of, I don't know, 0.8. These are lookup values. We use different resistance factors for different limit states. That's something we're going to be introduced to a little bit later. And so what we then might say is we've got, so let's say this is, I don't know, 800 pounds. Instead of using this Rn, this nominal resistance, we use a design resistance. I think that's like 640. And so instead of the 800-pound nominal resistance, we have a usable resistance of 640 pounds. And that's been reduced according to the associated uncertainty. So for example, and phi values are much easier in steel design than they are in concrete design. In concrete design, you have to actually determine your phi, right? Because if you have a reinforced concrete beam, the way that that beam fails is a function of the strain in the steel, right? You all remember this in reinforced concrete design, that if you have low strains in your steel, then it's compression controlled and the beam wants to fail in a brittle fashion, so you got a lower phi value. Y'all know what I'm talking about? I think you're shaking your head. Yeah, you know what I'm talking about. Okay. And so that would be resistance land. For loads land, what we might do is we might have a dead load of, I don't know, 100 pounds. We might have a live load of, I don't know, 300 pounds. Okay? And what we then, I've just made these numbers up because I don't even know if they work. And so what we then do is we say, okay, let's test a series of load combos. So we have a load combo 1.4 dead. We have a second load combo, 1.2 dead plus 1.6 live. We have a third combo, fourth combo, etc. And from these, we compute the maximum load. And as long as this design force, or this design resistance, is bigger than this factored load, we know the element is safe. So instead of applying a blanket factor of safety, what we do is we have a separate series of resistance factors and a separate series of load factors. So I want to talk a little bit about the loads and the load combinations. That's what I'm talking about here, where it says sum of gamma I, qi. The qi's are just, this is a q, that's a q, that, dead loads and live loads. And then the gammas would be like the 1.4, 1.2, 1.6, etc. Does that make sense? Okay. So here is probably the slide I would make sure that you can reference the most. This is on Blackboard, by the way, so you don't have to write all these down. These are the load combinations that we use in structural engineering or in LRFD. So I've highlighted the top 2 because I would say that those are going to be the most common ones that we utilize in this course. In fact, really the most common one is the second one, okay? But each of these load combinations are intended for different, what I would say, conditions of the building. So like, for instance, load combination 7 is for the building under extreme earthquake events, right? But really sort of when the building is evacuated. Load combination 6 is for earthquakes, but when the building still has like some people in it and whatnot. And there's a little bit of deceptiveness inside that because actual seismic loads and seismic analysis, there's a lot that goes on there. So there's a little bit in the background that's not really reflected. But it's like, for example, load combo 2 is more or less reflective of a general purpose use of the structure. Load combo 1 is probably more representative of a load combo that was controlled during construction because there's no live load. When in the life of a building is there no occupancy load? When it's being constructed, because there's no people in the building because the building ain't finished yet, right? So that's kind of the idea there, although we still need to check all of them and whatnot. Do you have a question? Oh. All right. Let's talk about the loads. Let's talk about the load types. And again, everything that's in these slides are on Blackboard and whatnot. Okay. In this course, my goal is to expose you to the navigation of a representative design standard in our industry. That design standard is the manual, the steel manual. But that's not the only standard we utilize in structural engineering. We use quite a few of them, right? We have the bridge spec, we have ACI 318 for concrete land, we have AWS for the timber design folks, etc. What about this? This is ASCE 7. Here you thought that ASCE was only a group where people built concrete canoes. ASCE does a whole heck of a lot more for the civil engineering industry than just sponsoring concrete canoe and steel bridge competitions. They also are a premier source of technical standards. ASCE 7 is one of the most popular standards referenced by civil engineers, period. And it delineates minimum design loads for buildings and other structures. And so that you're aware, like, here's kind of the point. What is the wind? Let's use a common expression. So winds are expressed in miles per hour. If you were designing this building, what wind speed do you think you ought to use? I'm asking. But here, let's just say here, right here. 40. Who thinks that's a good number?
I think it was like 90 or something.
Okay, 90. Who thinks that's a good number? This is admittedly a rhetorical exercise. You are engineers, and it is expected that you utilize your engineering judgment where appropriate. But that being said, there are folks that spend their entire lives helping to categorize and quantify design wind speeds based on a given location. Use ASCE 7. It will tell you the wind speed that you need to utilize for a given location. You get my point? You shouldn't have to guess what is the snow load that I need to use to design a building in Albany, New York. Look it up. You get my point? That's what these guides are for. They help engineers utilize a common standard for design of structures. Okay? Now, we're not going to reference ASCE 7 directly, but I kind of want to expose you to some of the basics. So let's talk about dead loads. Dead loads we are going to use quite a bit, and by and large they consist of a structure's own self-weight and any other permanent attachment. Dead loads are stationary. They are permanent. They do not move. The most common materials that we will utilize in this course and in most commercial civil engineering structures are steel and reinforced concrete. The unit weight of steel is 490 pounds per cubic foot, right? In U.S. units, what's the unit weight of water? Did that number get burned into the back of your head by Dr. Waite? Well, I'm going to burn these two in the back of your head. The unit weight of structural steel is 490 pounds per cubic foot. You can set your watch by it. I want you to have that number just burned into the back of your head. For concrete, so concrete's a little tough to standardize because concrete material weights vary. Concrete is a variable material, much more variable than steel. Normal concrete, normal weight concrete tends to weigh about 145 pounds per cubic foot. We usually up that to 150 to account for the rebar, because rebar is steel. Steel's heavier than concrete. So we tend to use 150 pounds per cubic foot for concrete. Unless otherwise stated, that's a good value to hang your hat on. Other materials and whatnot, we can, so let's take this building, right? So if I am designing the beams supporting this floor system and this ceiling, I would need the weight of the drop ceiling, the weight of the lights, the weight of the mechanical, the electrical, the plumbing, the weight of the concrete slab, the weight of the beams, the weight of the fire protection, the carpet. How do you think I would determine the weight of this carpet, like pounds per square foot? Well, I can look it up in a guide like ASC 7 because it has a lot of commonly available materials. What if carpet wasn't in ASC 7? How would I determine the weight of this carpet? Say it again? Well, you could weigh it, but if you're designing, you haven't bought it yet. Call the manufacturer. Just ask them. Those are commonly available data points that a manufacturer would have available. Live loads. Live loads are related to a structure's occupancy. So we have different live load values for what a structure is being used for. We have different live loads for theaters than we do for hospitals, than we do for office buildings, etc. So for this building, we would utilize different force effects for the classrooms than we would the hallways, etc., because that's what they're used for. Now, let me ask you a question. This is a very common load combination, 1.2 dead plus 1.6 live. Why is this number larger? Because it's more variable. I have more uncertainty associated with the live loads than I do the dead loads. Dead loads is all about just computing volumes and unit weights of materials and just adding everything up. The uncertainty comes from, like stuff like you got an 8-inch slab, DOH, and they might pour 8 1/4. They might bump it up a little bit just to make sure they get their target depth, right? That makes it a little heavier, right? But that's what the factor of safety is for. That's what the load factor is for, to account for additional load, for uncertainties. But the live loads, I got much more uncertainty about that. So I'm going to up them 60%, where I might up the dead loads only 20%. Does that make sense? Everybody okay with that? Any questions? All right. Let's talk about snow loads. So snow loads are dependent on where you're at in the country. And so if you open up ASCE 7, you get this like mess. I mean, let me be clear. This is a highly calibrated map based on available, snow load data across the country, and it is continuously refined and whatnot. But to view this on an 8.5 by 11 sheet of paper, it's kind of tough to read. So a lot of times engineers will use tools. This is a really cool tool where what you can do is it sort of integrates with Google Maps and whatnot, and so you can put the address of, I'm building Geico's new corporate headquarters, and it's going to be in Fairfax, Virginia. So I can put the coordinates, the street address for where the buildings will be, and it'll figure out, it's right there. The snow load is 25 pounds per square foot, something like that. Now, what happens with snow loads, I hit the button. What happens with snow loads is that the spec reports ground snow loads, because that's all it knows how to do is how much snow is on the ground. You must then convert that into how much snow accumulates on the roof, right? And I'm not getting into the weeds on structural loads. I could teach a whole class just on how to determine loads on structures. But there are adjustments that you need to make to your snow load dependent upon the type of structure. Is your roof flat or is it angled? What type of building is it? So what do you think would happen if I was designing a greenhouse? How would that affect snow loads? What do you think? What's going on the roof of a greenhouse? It's hot. And if the roof is hot, what does that do to the snow loads? There you go. So the snow loads go down. The type of structure affects what you're dealing with in terms of loads. Your environmental loads also change as a function of what's called the risk category. Do I have risk categories here? Oh, no. Let me just sort of mention risk categories. So ASCE 7 defines 4 risk categories, and the risk categories are used also to augment some load. So let me give you an example. Risk category 1 is basically unmanned structures like grain silos and empty warehouses and things like that. They do not have as much of an impact on society as like a risk category 4 structure. Risk category 4 is a structure that if it were to fail would have a profound impact on the surrounding community. So risk category 4 structure would be like a hospital. a fire station, a police station, et cetera. So when we as structural engineers are designing risk category 4 structures, we bump the loads up because of that importance category. Risk category 2 is basically like any structure that doesn't fall into the other categories. Risk category 3 are structures where the occupants in the building might have a hard time getting out on their own if something were to happen. So risk category 3 would be like a nursing home or a theater, because there's a lot of people in the building all at once. So does that make sense? So yeah, just want to throw that in, out there for you. Now, wind loads. Here's the deal with wind loads. This is the wind speed map. The previous spec used 90 PSF or 90 miles per hour for the wind speed, but that has been augmented in recent specs to 115 because the uncertainty factors have actually been built in to the number. In fact, if you look here at your load combos for wind, a lot of the wind ones are 1, because the idea is that these values are sort of already factored. That's kind of the idea. Now, the vast majority of the country has a design wind speed of 115 miles per hour. What's going on the coasts? Why do the coasts suddenly get larger? Why do we have higher wind speeds on the coasts? Hurricanes, there you go. So exactly, as you start getting closer to the coast, you have to up your wind speeds because of the potential for hurricanes and ocean storms and whatnot. The other thing that's about wind loads, and this is about both lateral force effects that we have to deal with, wind and seismic, they are adversely impacted by the height of the building. See, when you're designing for gravity loads like dead load and live load, designing a floor beam on the 2nd story is exactly the same as designing a floor beam on the 82nd story, because gravity load doesn't change. But as the building gets taller, the lateral forces tend to get larger. So the lateral system for this building doesn't have as much oomph as the lateral support system for Smith Hall, because it's a taller structure, right? Does that make sense? Like, we might have actually a bigger lateral support system because we just have a really, really big building over here, but, you know, pound for pound, that's going to be a much stiffer system. The other thing I do want to mention, and I just want to sort of highlight this, is seismicity and seismic events. A lot of times we really don't think about that here in West Virginia because we don't get a lot of seismic risk and whatnot, but you'd be surprised how close some of the adjacent fault lines are and how we have to account for high seismic risk in areas very near to us. So in western Kentucky, for example, western Tennessee, we have some pretty high seismic risk category because of the location of the fault line there. So we have to consider seismic events, even if the probability of that earthquake going is low. If it does go, it's going to go. Now, one of the things about seismic events is that there is no earthquake monster pushing on the building. It's not like snow or dead loads where there's actually a force applied. The load comes from the building's own inertia, okay? Now, it also changes how we as structural engineers handle these types of events. Let me ask you a question. You're in the car with a friend. Your friend doesn't know how to drive. They're driving 55 miles per hour. They slam on the brakes. What's the first thing that you hit?
The dashboard. Seatbelt.
Who said dashboard? Wear your seatbelt. But here's my point. We do not, well, here's my 2 points. Number one, wear your seatbelt. Number two, we do not design the entire car to restrain you during a collision. We install a specific system inside the car to hold you back. It's not the whole car, it's just a subsystem of that car. We call that system a seatbelt. We install seismic bracing inside buildings to hold the building back for an earthquake. We also have lateral resisting systems for wind as well. It's not the whole building, it's a subset of the building. And so, like lateral design, there's probably only a few beams and columns in this building meant to hold up under lateral events, not the whole building. So, something to keep in mind. And yeah, just something to keep in mind are some of the seismic risks and whatnot in the area. Again, I'm really not getting into the weeds on how to compute these loads, because that could actually be an entire course in itself. I just want you to get kind of the concepts, because in here I'm more interested in the design according to steel structures. And we'll cover the basics of load estimation with some of the problems that we deal with in here. Any questions? Your homework. You got a series of loads, factor them, get the worst case factored load. That's all you got to do. I'm not going to see you in person until next Wednesday. So what's going to happen? Friday, it's going to be a live lecture, or a lecture on YouTube. It's going to premiere Friday at 11. Do that assignment when you got your manual. It will take you 5 minutes to do that assignment. It's not a lot. Until then, see you all next week.